In the second lecture, I'm going to concentrate onto the application of single molecule tracking. Yes, in the last lecture, I told you that the single molecule tracking is based on the time evolution of the fluorescence image, and we can get, by applying the localization method, we could get such trajectory of molecules. And I did show you the analysis of translational motion, provide us the information of the property of polymer matrices. But not only the translational motion, but also the rotation can be detected by single molecule tracking. This is based on the dipole moment of the emission. Yes, please imagine this is a molecule, and this arrow shows the transition dipole moments of the emission. Yes, in the classical way of treatment, the emission or light emission can be regarded as the motion of the electron inside the molecule. So if the electron is moving in this direction, light or emission coming from this molecule is polarized in this direction. So if we can get the polarization of the light coming from the molecule could be detected, we could get the information about the orientation of the molecule. And for the detection of the polarization, some specific method was developed by these persons. This is called as defocus imaging. This picture shows you the fluorescence image of individual molecules. And yes, this spot size is, as I told you in the last lecture, is about 200 or 300 nanometer in diameter. But this is obtained by the focusing is perfect. But if we defocus the lens, yes, we could see such a strange image. And this is coming from the electric field coming from, originating from the molecule. And this is a dipole moment, a transition dipole moment direction, and this theta is the angle. And of course, phi is of course the angle. But anyhow, the shape is dependent on theta and phi. So if by analyzing these images, we can get the information about the orientation of the molecule. And as a result, we could see the rotational motion of the molecule in the single molecule level. And as an example of the images, I would like to show you some molecular motion in polymer film. This slide shows you the samples we used in the experiment. This is a fluorescence molecule and with large size, and the emission will appear around 550 to 650 nanometer. And these chemical structures shows you the polymer host. PMMA and PMA are used in the experiment. But the glass transition temperature of PMMA is much, much higher than the room temperature. Glass transition temperature is a temperature where the polymer will become soft from hard shape. Anyhow, yes, of course, we should say glass transition definition of the glass transition temperature more precisely, but roughly, yes, you can imagine that above the glass transition temperature, polymer is very solid, is very soft like rubber, and the molecule inside can move. But below the glass transition temperature, polymer is very hard, so the molecules inside cannot move. Anyhow, this is higher than the room temperature. The glass transition of this polymer is lower than the room temperature. First, I'm going to show you the result in PMMA where the glass transition temperature is much, much higher than the room temperature. This is a video which we could observe in PMMA, and each spot shows the emission coming from the individual molecule. With an increase in the time, the video, you can see the decrease in the shining spot. This is due to the photodegradation of the fluorescent dye. In this kind of experiment, we are using very strong laser light. So the fluorescence dye will be broken time by time. And you sometimes find, you can find sometimes blinking of the fluorescent spot. A shining spot once becomes dark and then starts again. This is due to the transition to transient non-emissive state. But apart from these observations, you can clearly see that the guest molecule was not moving. Yes, for example, this molecule, yes, the direction of this image doesn't change. So it keeps its orientation and position in the translational motion. This is a result in PMA. PMA, as I just told you, PMA, glass transition temperature of PMA is 10 or 15 degrees lower than the room temperature. So the polymer host is very, host is not so hard. So you can see, for example, this molecule, rotation or orientation angle is changing time by time. So this is due to the low glass transition temperature. And this slide shows you the time course or time evolution of the orientation of one molecule. At 0 second, the direction is along this arrow, and 3 seconds, 6 seconds, 9 seconds, 12 seconds, and 15 seconds, yes, the direction is changing. This is due to the rotation of the molecule in solid field. And of course, this is due to the low glass transition temperature of the host material. This slide shows you the distribution of rotational speed. Yes, x-axis shows you the angle changed in a unit time, yes, velocity of rotation. And y-axis means the number of the event. For example, this molecule undergoes rotation, with various speed. But this molecule is a little bit calm, or compared to this guy, this molecule stays in at this position, not so rotating. But this molecule shows very largely rotating. And what I want to emphasize from these figures is very simple. Even though the molecule is the same, yes, the same means that the kind of molecule is the same, and these are embedded in the same polymer field, but still we could see such a difference. These are coming from the heterogeneity or inhomogeneity of host materials in amorphous environments. So I'm going to show you another example, but used to investigated by the single molecule detection in translation and rotation. Yes, this is a material which is called as organosilica mesoporous materials. As this is a electron microscope image, and as you can easily see, yes, very thin tunnel is aligning in this material. And this is a side view of this material, and we could see, yes, many tunnels are composed in these mesoporous materials. And this is developed by a Japanese scientist many years ago. And these materials have been attracting much attention for the transportation of the molecule in the mesoscopic scales. And in this tunnel, to evaluate the translation of the molecule inside the tunnel, we put fluorescence dye in this tunnel. This is a dye used in this experiment or this investigation. Long shaped fluorescence dye, and it is inside the tunnel, and we can get single molecule motion in translation. Actually, we could see the molecule is moving and along with a one-dimensional tunnel. And in this case, we can see molecule motion. In the beginning, molecule is in this channel, but later, molecule moves in this tunnel to another tunnel. So we could directly see how the molecule is moving along this one-dimensional channel. Yes, not only the translational motion, but also we want to know how the molecule is moving in the tunnel. Yes, we are using a very, very long fluorescence molecule. And yes, we used defocus imaging, how the molecule is moving. Yes, this is a video. And you can see that the molecule is moving in this way. First, we thought this molecule is long, and so molecule is moving, lying in the channel. I mean, yes, not standing and lying and moving in this way, but the case is not the same. This is not the case. In this case, a molecule is standing in the tunnel and moving in this way, never lying and going. But this information is obtained by, yes, only by the focus imaging. Anyhow, we can get such information on the motion in the tunnel by using a single molecule detection and rotation and translation. This slide shows you the summary of my talk, and I did tell you how to detect the translation and rotational motion. And the focus imaging is a very powerful technique to get the information on the rotational or orientational motion. And we can get information about the application. And I did show you the results in the polymer films, motion in the polymer film with the glass transition temperature higher and lower than the room temperature. And I did show you how the molecule is moving in the tunnel of the mesoporous material. And I hope many of you have some interest for this kind of experiments, and I'm expecting you to join the research. You to join the research with us. Thank you very much for your kind attention.